Hello, here's our group's video on the external fluid dynamic capabilities of SolidWorks. Um, and to make it more fun, instead of using an airplane or an airfoil as you would normally use this software for, we're going to show it with a cow because it's way more entertaining. So to begin, we'll go over to tools here and go over to the add-ons, where you'll come on down and hit this check mark for the Flow Simulation 2025. Once that runs on through and drops down the toolbar over here, go to Flow Simulation and access the wizard immediately. In this case, we're going to be recording it for a 40 miles per hour case, but I will also be recording an 800 mile per hour case for laughs and whatnot. But continuing on, we're going to do it in USA units, and then also drop the velocity to miles per hour instead, just so it's more standardized across the other simulation that we're going to be showing in Star CCM. So continuing on the trend here, we're showing a fluid flow over the surface, and we're also going to include gravity in this case. And something very important too is that we're making sure that the gravity is pointed in the correct direction down. So in this case, it is in the Z direction, pointed down from the cow. In some cases, depending on how you orient the original model, you'll have to modify it. Continuing on, we're going to just go straight to gases and use air, and double click that. So air is the project that's being used in this case. That'll be flowing over the cow as it's flying 40 miles per hour through the sky. Continuing on, wall conditions would really be useful if we had the cow on the ground and wanted to replicate the image from the beginning of the presentation here, but we're just going to skip on by that because it's flying in the air. Then moving on to velocity. In order to actually demonstrate the velocity going in the right direction of the cow, we treat the cow actually as a solid object that doesn't move, or a fixed object, and we have the velocity going in the y direction, as we can see here from the axis, going in this direction. So it's 40 miles of wind going, 40 miles per hour of wind going past the cow. So once we have that all wrapped up, you can also kind of tell too that we care more about the backside of the cow with its flow, as you will tend to analyze the flow of things after they've been disrupted, after the air gets disrupted by the actual fixed object there. But moving on to figuring out stuff with the cow, we're going to go over here to the mesh and insert a local mesh on the area there. We're going to have to probably spend a second messing with the exact values that we need, but in this case, because we're just using external, we'd want to do equidistant refinement. In this way, we're breaking down more refined squares around the actual cow itself, the closer that you get to the cow's surface. Also, a little fun fact, the cow is about the size of a fingernail due to the Sketchfab file, and there'll be something else that will also be mentioned about that in just a second. So going over to here, I believe, aha, wait, no, there's another 0 there, another 0 there. And then make it get more refined as we go along. We also have to select the correct body to actually go around the cow within the actual chamber itself that we're testing in. So if we go over to the simulation and have it run itself, which I am trying to remember how to do, create mesh, there we go. Creating the mesh itself shouldn't take a very long time, as this little pop-up menu will come on up and see how quickly it goes through. We can then have a little drop down of a cut plot in the right plane, which can show the mesh in detail. So as you can see, as we get closer to the cow itself, the mesh becomes more refined, which we will use to our benefit when it comes down to the analysis that we'll be showing here in just a bit. But going from here, we're going to want to make some goals that relates to what conditions we're trying to find. So in this case, we're trying to find the velocity for the z direction in terms of its average, as we want to find the total lift within the actual lift on the cow, and then we're going to want to plug in the velocity for the y direction, as well as a global goal for the variable to converge on for the drag that's behind the cow. So once we have both of those in place, we'll run through the, since the mesh is in place and the goals are there, we would normally, to limit the amount of computational time that it would take to, what do I want to say, the computational time that it would take to actually do the computational fluid analysis, you would normally put a subdomain and break the cow in half pretty much. But as you can see, the sketchfab file that we used didn't really align with the axis, and it wasn't cooperating when we tried to rotate it. So I messed around with it instead, and we're just going to be doing a analysis of the whole thing. Which is a bit more inefficient. So now we're going to go up here to run, since the whole thing is working as it should be. Click run, and we'll have it go through. As you can see, the solver might take a second, so this is where we're going to skip the video, and just because of how long the process takes, we're going to cut right about. So coming back after 297 iterations, here is the solution that we converged upon. So with the diligence of these cut plots, which you can add as soon as the results of the actual solution are finalized, which are super simple to insert, as you just go over here, and then if you want to have it in just the same plane, so in this case it'd be the YZ plane, and then going down here you can choose from a plethora of options within contours. So in our case we chose temperature, pressure, and velocity. Looking just at the velocity, these are features that we would expect from a CFD simulation. If you were to put a cow, I guess, at 40 miles per hour in the sky, where it's higher near a lot of these sharper edges here, and you can actually control the slide of the actual cut plot over here. So if you just want to go towards the legs and then back towards the front of the body, we see that the velocity speeds up, especially around the head and especially around the lower body there, and also seen at the ends of its legs, which is what we would expect. And then we would also expect the lowest velocity to be right behind the legs, as the speed is blocked by that object flying through the air. So then just going over and showing the temperature as well. These are things that we would expect for the actual surface to be hotter than the surrounding air around it, and to shed that heat around it as the cow is flying through the air. We can also look at the pressure, which doesn't really tell much at this point, as the cow is not exceptionally aerodynamic at all. Regardless, I think my computer is now having issues, so that's super cool. But as you guys have seen, using computational fluid dynamics through SolidWorks is very fast and simple to use. It's pretty intuitive, and look at that, SolidWorks had a problem. That's amazing. And we'll just see how the results from this hold up in Star CCM. So